we have two talks. Our first talk is by Dr. Shams Basir. He would be talking to us about fixing physics-informed neural networks. And a little bit about him. He's a senior manager and data scientist at Bristol Myers Squibb. He obtained his PhD from the University of Pittsburgh and has a dual BSc degree in aerospace and civil engineering from Middle East Technical University, Turkey. His research interests include scientific machine learning, optimization, computational fluid dynamics, and high-performance computing. With that, please join me in welcoming him for the presentation. Please take it away.
Thank you so much, Samdata. Thank you. And again, it's a pleasure and honor to be here to speak with, as Professor George calls it, pinheads. So yeah, as you can see, the title of my talk, fixing physics-informed neural networks. And like some of you may know, the old saying that goes, if it ain't broke, don't fix it. So we first of all try to figure out what are the things we could fix, and then we'll propose approaches and methodologies to fix it. So I want to give a shout out to my PhD advisor who collaborated and this material with me. And with that, let's get into essential keywords. So I want to establish a common language with the audience. And so if you know these keywords, you should have an easy time understanding the talk. If not, no worries. So the gist of the talk, some common keywords that you'll hear is composite objective function or multi-objective loss function, loss functions that have several terms. And then you'll hear twin models or paired models, where the models are identical in terms of architecture, optimizer, and the rest. And then you'll see some loss landscapes, means we'll look at the geometry of the loss. And I'll speak about optimization under constraints. And you'll hear me talk about maximum likelihood estimation a little bit. And then you'll hear me say auxiliary variables, means helper variables that I introduced that are not in the problem. And then obviously the forward and inverse problems. And so for folks who are not familiar with what forward and inverse problem is, forward problem is basically you're giving your model some input setting and you're trying to figure out the output of that process. And inverse would be the opposite. So some context. I know these things might be repetition and you all might be familiar with this, but for folks who are not familiar with partial differential equations and stuff, I want to say that a lot of processes in nature and engineering systems, they have some sort of transport of mass, heat, and luckily they can be described by beautiful mathematical equations we call partial differential equations. And so the solution of these PDEs often cannot be found analytically other than some ideal canonical situations. And so what people do is they rely on numerical methods, finite difference and finite volume and finite element, to name a few. And as you can see, all of these methods start with the word finite, means you're discretizing your domain into finite number of elements, cells, volumes, and whatnot. All right, but the quality of your mesh highly affects the quality of your solution. And especially if you have a problem that is evolving in time that might require you to generate your mesh or grid at each time point, then that would be really tedious and time consuming. And for inverse problem, these conventional numerical methods are not straightforward to apply. So with that, we want to say that people have thought, oh, what about artificial neural networks? Well, why? First, they're universal approximators. They're shown to be able to represent any function, continuous bounded functions. And they could be thought as mesh-free methods. I like this feature of neural network. Well, that's because you could apply it to any complex geometry, and they have the potential to break the curse of dimensionality. If you're generating grid, for example, if you have a one-dimensional problem, you generate, let's say, 10 segments. And for 2D, you might need 100. And you know where I'm going with this. So as your dimension increase, the number of elements you need to cover your space would scale exponentially with the number of dimension. But with neural network, because we're not generating mesh, we are randomly sampling collocation points, we're hoping we break the curse of dimensionality. And so once these models are trained, they're basically functions. You could ping it with any coordinate and get an output. And as long as you can create an objective function, it doesn't matter if you're solving a forward problem or inverse problem. From that perspective, they're very efficient. And Anything you could do with conventional machine learning, you could do with these models too. So one particular thing I want to mention here that I haven't seen yet, let's say you're creating a DNS simulation. And so you might need to save all of that output somewhere in a database. But what if you had a large neural network that could that could embed all of that data in its weight? And so anytime you need some data, you just ping the model and get the data instead of like saving all the outputs for that fixed simulation, right? So you could do all kinds of things with these models too. So those are also like some cool features. But the problem is that neural networks are data-hungry models. And so, but for scientific application, you may not have the luxury to have data, or in some cases, it might be even impossible to obtain this data. And unlike conventional machine learning, like let's say image recognition, where if you have a model that is recognizing images 90% of the time, that could be a good model to deploy in the real world. But for scientific application, you have strict conservation laws. And if your model is, let's say, conserving 90% of the mass, it's possible that model is outputting junk. And so that's a really important thing to note. And let's say you do have data. You may have data that are high quality, low quality. And so you don't want to like treat these data equally. If you do, then it's possible you're either overfitting the noise or underfitting the more clean information that's embedded in the high fidelity data. So the thought is, okay, let's train these models with physics regularization. So like I mentioned in the beginning of my talk, that you would hear me say twin models. So why do we care about these twin models? The reason is that we want to build this a baseline model, and it's twin physics informed neural network model. Why? Because we want to compare these two models and see what happens when you embed physics. What happens to the loss landscapes, how the model learns, what issues you'll face, and how we could mitigate those things. And so for that reason, I'm here creating a simple regression model with a composite loss. And this composite loss is basically this, which has the loss for the boundary and the loss for the domain. So I'm assuming you have this domain where you have labeled data and you're trying to fit that function. So like I said, the reason I separate these two is because I want to create twin models to be able to understand what happens when I change this domain loss to a physics and see what happens. So that's the reason we create an objective function that's composed of two loss. And now one thing I want to point out here is that these two loss, they have the same physical scale. It's the u minus u hat. They have the same physical scale. The only thing that could imbalance these two loss would be the denominators, which is the number of points. So now let's go to the physics informed model. And this is a pioneering work by Raisi and Professor George's student and Professor George's lab. And so the idea is that, okay, now I don't have labeled data, but I have some operator. I have some physics, some governing equation, some partial differential equation that I know the output of my network should satisfy. And now, instead of the labeled data, we just switch it with physics. But what are the issues here? So the issues are that these two laws now have different physical scales. And so you're probably thinking, so what? Well, you're training your model with some sort of gradient descent. And if you look at the unit of the model's parameter, which is theta, it's the unit of its the gradient of the loss with respect to theta, assuming that your learning rate, which is eta, is unitless, right? So if you have several objective functions with different physical scales, the model has no knowledge of the physical scale. It's just looking at the number. So maybe you have 0.3 kilometer and 100 millimeter. To the model, it looks like 100 millimeter is way more important than 0.3 kilometer because the model doesn't know the scale. You're just combining these different physical scales together, trying to create an objective function. So and then your model may either sacrifice the physics or the boundary condition. Either case, you would get a junk solution. And among these related works, there is a work by Lagares and colleagues. So they're proposing a slightly different approach. They're saying like, hey, I don't want to create an objective function separately for the boundary and for the domain. I want to create a trial solution that would automatically satisfy the boundary condition. Now that's a good idea, but The issue is that you could create infinitely many trial functions for a particular solution, for a particular model, right? How do you know which of those trials function is good, is optimal? If you don't get the solution, you really have no idea whether it's due to the optimization or it's your trial function that is the problem. And you cannot create these trial functions for complex geometries and for problems where you have sparse, information. So that's the challenge. Now you know the issue. So we want to test it on a very simple one-dimensional Poisson equation. And this Poisson equation, we assume a sinusoidal solution because I can increase the complexity of the solution and see what happens. And these are my training configuration. Like I said, these training configurations are fixed for all of these models, because that's why I said I create twin models. So then we look at the different oscillation. So for oscillation omega equal 5, I see that my data-driven, my regression model, where I feed the model the exact labels, has like 10 to the minus 2 relative error. But my PINN model has 10 to the minus 4, which is almost 2 orders of magnitude better. That's great. But then as I increase the complexity of the solution to omega 15, my PINN model fails. So I know that the only thing I changed in my objective function was the physics loss, the domain loss that I changed from labeled data to physics, and that's it. Now we look at the loss landscapes. So what are these loss landscapes? First of all, we cannot possibly visualize the high dimensional loss landscapes because these models would have like, I don't know, hundreds and thousands of dimensions, and we humans, we could only see 3 dimensions. So the best we could do is we could cut or slice the high dimensional space, you could think, and get a surface that includes the point your model converged. And you only look at that surface in the neighboring point of the location where your model converged. So that's the best we could do. And that's what we do here. So we just look at the neighboring points where the model converged and see how the loss landscapes look like. So for omega 5, our regression model has these nice loss landscapes. And this is the point where the model converged. And so we see that, there's a clear minimum. And it goes similar to all these omegas, omega 5, 10, 15. But for PINN model, as we increase omega, the loss landscape gets pretty chaotic. And so there's no like clear minimum. And so we see that as we increase the complexity, this imbalanceness between the loss terms increases, and that translates to the loss landscape where the model fails. And now people thought, oh, okay, what about we multiply these two objective functions with some weights to balance the objective, these terms. Now that's a great idea. That's a great idea. But if you're solving a PDE, you don't have no data. There's no data. So for you to know what these lambdas are is almost like impossible. If I give you a solution, a problem, and say, hey, figure out the solution for this, you wouldn't know what lambda I should pick. But unfortunately, in our community of physics and neural networks, a lot of people say, oh, this is my hyperparameter, but you don't know the solution. If you know the solution, what's the point of any solver, right? So we're trying to figure out a neural network-based solver that can solve things for us. If I know the solution, I can just tune these lambdas to fit the solution to the PDE, then there's no point, right? So we're trying to get rid of that and come up with a method that would not rely on this manual tuning. And there's been a lot of work that highlighted this issue, and they've proposed their approaches here that, in the interest of time, I may not go over all of them, but if you have questions, I can happily discuss. So I'll discuss one of these methods just to highlight, if you want to propose your own method, what you should consider. So this is a work proposed by Wang and colleagues. And so they say, well, if you have an objective function that's given in 1, what you could do is you could come up with those lambdas like this, like given in equation 3. But the one thing that we should note is that if you're converging to a local minima, you should satisfy the optimality condition. And, let's say you want to find the maximum, the minimum of function, the derivative at that point should be 0, right? And so regardless of what you do, how you come up with these lambdas, they have to satisfy that optimality condition. Otherwise, you would land somewhere and you think that that's a local minimum, but that's not. In reality, not, because your loss function is not theoretically satisfying the optimality condition. And so, and also you want to carefully incorporate the quality of data here, because if you have noisy data and you're trying to come up with these lambdas, then you're fitting the noise in the noisy data. So to summarize, we just showed that we discussed it, that if you're solving for a problem where you don't know the solution to the PDE, where you don't have data, there's no way for you to tune these hyperparameters, which in machine learning people do using validation data set. And so, and also, even if you like come up with your empirical approaches or somehow come up with these lambdas, then you're still soft constraining. And like I mentioned in the beginning, scientific problems, they have strict conservation laws. And so if you have noisy data and high fidelity data, you want to take care of that too. So now all of these things could be defined in a mathematical way, right? So let's say you have some noisy measurement data, and you know your PDE, you know your high fidelity data, you know your boundary condition and whatnot. So how can you come up with a loss function that is embedding the information in your noisy data, that is satisfying your PDE, and that is strictly satisfying your high fidelity data and your boundary conditions and all of that? So for that, we proposed what we call physics and equality constrained artificial neural networks, and they're nothing but a loss function that's grounded in constraint optimization. And so now all we do is, again, for the physics, you do the same thing. You ping your residual PDE with the coordinate of your space. You get your loss. You sum it up. That's your governing PDE loss. So first of all, we're building the pieces of the puzzle, and then we're putting it all together into a constraint optimization problem. So this is one piece of the puzzle, the loss on your PDE. All right, and then now think of the noisy measurement data. So it's very simple. What do? You could do a maximum likelihood estimation, right? Once you do the maximum likelihood estimation, you come up with this formula. And these sigmas are the standard deviation of your noisy data. And if you don't know these sigmas, no worries at all. Why? Because you could take the derivative of this with respect to sigma, and you would come up with an explicit formula for sigma. And you could update it during your training. And so now you may have several different quality of low fidelity data that you could just combine together, and each of them would have their own sigma, and you can update it during your training. No problem. If you know it a priori, just plug it in there. All right. So now that we know the loss function for physics and the loss function for your noisy data, how can you constrain your high fidelity data? So just to show the algorithm, I assume that the boundary operator is clean, noiseless, but it could be high fidelity data, no problem. So what you want is actually, you want to minimize the objective of your physics and your noisy data, but you want to strictly constrain conservation laws, high fidelity data, all of that. So what you could do is you say, my residual has to be between minus epsilon and plus epsilon, which is good, right? And if you think about it, we care about the magnitude of the residual, not about the sign of it, right? So we can introduce this convex function and say, well, this convex function, like it could be an absolute value, a quadratic function or whatnot, and then and define this, right?
What is the B operator? Did you define it?
Yeah, it's boundary operator.
Okay.
Yeah, so I assume that boundary operator is clean, but it could be high fidelity data where that B would be U minus U hat. So it's just like for representation purpose. And then you could say, well, I want to really shrink my margin of error and push this epsilon to 0, so you would get this. And now you have your equality constraint. So then, okay, all right. So then you could put all these pieces together to formulate your constraint optimization problem. And it's nothing but minimize the residual of PDE, the residual of your noisy data, subject to the constraints, which could be high fidelity data, noiseless boundary, and whatnot. All right, now that you have this constraint optimization problem, what you could do with this is that you could use either the penalty method, Lagrange multiplier method, or augmented Lagrangian method to convert it into a loss function that you could use to train your model simply. And then we could also
excuse me, can
Sorry.
I ask a quick question?
Sure.
This is Panos Tinis from Pacific Northwest National Lab. Can you go back to the previous slide?
Sure. Why is this? Okay. Oh, here you go.
So in this, I see this constraint optimization. However, the problem that you mentioned before, that you may have different scales, has not been addressed, because the JR, which uses the residual, and the JM, J sub M, which uses the data, could be at very different scales. So you still have the issue of the stiffness that you could get when you try to do gradient descent or something.
That's a great question.
Yeah.
Yeah. So you have these sigmas down here. And what happens is that once this sigma, you either learn to update these sigmas during your training, or you know the sigma, you put it in there, and the more you train, this is your objective function, the lower your training gets. And also you would still have that issue though. You would still have that issue that you're mentioning. And in our follow-up work, we're actually tackling that. That's a great point.
Okay, because the sigma, the issue with the sigma is something different, right? You could have clean data. So sigma is 0, so you don't have to use this formulation for J sub M.
Yeah.
And you could still have the scale for the data term to be very different from the scale for the residual term.
True. If you have clean data, you're no longer using the maximum likelihood estimation. You
No, I know, but then you would still have, however, the data term, right? That you have to satisfy the data. Yeah,
correct. You're absolutely right. In our follow-up work, what we actually do is for inverse problem, we minimize the residual on the noisy data only, and we constrain the PDE. So we do a PDE constraint inverse problem. And turns out that that works better than this.
Okay, all right, thank you. I don't want to.
Thank you. That's a great question.
Thank you.
Can I ask a question too?
Sorry, is there a question?
Yes, this is Jerome Dabon from Brown University. Can I ask a question?
Sure, absolutely.
How do you know that the constraint is not empty? How can you make sure that there is a feeder, the existence of a feeder, such that it satisfies the constraint? In other words, how do you know that the constraint is not the empty set?
I did not get the question. Are you asking about this?
Yes. Here you need because you need to find a feeder, at least one, such that the constraint is validated. How do you ensure that you have the existence?
So if I understand the question correctly, you're asking, how do you find theta that makes sure that this constraint is satisfied?
Yes, at least one.
Oh, okay. So let's go back to our problem here. In the beginning, I said you could define your constraints like this, and your constraints would have a margin of error. It could be in the range of minus epsilon to plus epsilon, right? Then I said, well, we don't care about the sign of the error. We care about the magnitude of the error. And so I introduced a convex function phi, which could be like you could define this as an absolute value, right? Or as a quadratic function. And then I said, well, now push the margin of error to a very small, tiny epsilon, which approaches 0, then you would get this equality constraint.
No,
so
I get that.
Is nothing.
But I get that. But even for the problem, when you have minus epsilon, how do you know that the constraint is not empty?
Oh, how do you know that the constraint is not empty?
Yep.
So you mean like, how do we know we don't even have a constraint?
No, I mean, maybe the constraint, there is no feeder that satisfies this.
I still don't understand the question.
Okay,
we
can talk offline then. Okay.
Yeah,
I'll be happy to discuss this after the talk.
Yeah, Shams. I think what Jerome asked is, how do you guarantee that there exists a theta such that this constraint is satisfied?
Oh,
So, yeah, whether the optimization problem has, the existence of the theta that satisfy the constraint. I think that's what Jerome asked.
okay. If that's the question, that's a great question. We don't really, that's a pretty much neural network. Its mathematical underpinning is really hard to explain. So for neural network, it would be really difficult to know, like, is there a phi? Because these are all non-convex optimization problems. It's hard to know, like, if there is a theta, if the theta exists that could satisfy this whole thing. So at the minute, we assume there is, because it's mathematically difficult to prove that for a neural network, which is like a non-convex optimization problem. But that's a good question. We don't do that right now. So we assume you can find a theta. There is a theta, because we're initializing a neural network model. If that's the question, we don't know if there is a theta that satisfies that.
Okay, thank you.
Yeah.
Thank you.
Wouldn't that just follow from the universal approximation theorem?
Yeah, but in universal approximation theorem, you're only showing that your network has the capacity to represent the function. You're not showing whether you can learn it. Because if you could show that, then the machine learning field would be done, right? You learned everything. That's the whole issue. You can show that you can represent it, but can you learn it? That's a different problem. Learning is a whole different thing than just showing that this network can represent the function. All right, I hope I answered your question. So, okay, so once you have your constraint optimization problem down, then you could use any of these methods to write an unconstrained unconstrained loss function, and then you can use it to train your model. And now how you do that? Well, once you, so the problem is a two-step process. We use here the augmented Lagrangian method because it combines penalty and Lagrange multiplier method, and the detail of this is discussed in many optimization books. And in the interest of time, I don't want to go there, digress there. But now the cool thing is that once you have your loss function down, you could update these Lagrange multipliers. You no longer need to tune them. And they also make sure that your constraints, the defined constraints, are strictly satisfied. And this penalty is a positive number that you start from a small value up to a large value, and you increase it during training. And in our follow-up work, we found out that updating the penalty also has a very important role in converging the model, and we have methods to tackle this as well that didn't make it to this presentation, but I'd happily share it as soon as it comes out. So then, with the same network, same setting, all we do is we just formulate this objective function, like I mentioned, and we train the same network to see what happens. Turns out that if you constrain, so for this one-dimensional Poisson equation, you have only the boundary condition. So that's it. And so we constrain the boundary condition. And we see that as we increase the omega, the residual, the error levels are way better than the PINN, and one level better than the data-driven model. So if you see, the data-driven model pretty much have the same level of accuracy for all of these omegas. But and also the PINN, the accuracy goes down as you increase the oscillation, but the model still converges. So here we're trying to show that if you properly formulate your constraint your problem into a grounded bit on a constraint optimization, then you have a better chance of learning the underlying solution. Is there a question?
I have a question. Yeah, the paper by my former student Lulu and Steve Johnson from MIT on the hard constraints is exactly like that, the augmented Lagrangian.
Yeah, I do see that, and I did cite it in my paper. So what they do is they create trial function that the boundary conditions are automatically satisfied, and there are some
No, but it's not a matter of, it's a constraint in general. It's not just a boundary condition. We're talking about a constraint. Constraint have actually a volumetric constraint, which is more difficult to satisfy than the boundary constraint. So they use the augmented Lagrange, and that works also for them.
Yeah, sure. Yeah, absolutely. Yeah. But for this problem, we only had the boundary condition to constrain. It was just like a test problem, and that's it. But you could have other constraints, like, conservation laws and mass and all that stuff. So then we look at the loss landscapes for this way of formulating the objective function. And it turns out that as you increase the complexity of the solution, you still have, even though your loss landscape is getting like rough, but the optimizer was still able to find out a good minimum. And so that shows us that by properly formulating an objective function, you have a better chance of learning the solution to your PDE. Of course, this is not the ultimate solution. You could, like I mentioned, you could have like better update group for the penalty, better formulation, robust formulation for large scale problems, and all that stuff that we will hopefully in our future work discuss. And now here we showed for a two-dimensional Poisson, and the objective here is to show like, okay, your geometry could be complex, and that's it, like, because you don't create trial function and the geometry can be complex and you could still apply this approach. And yeah, so that's that. In the interest of time, let's move from this. And this is a benchmark problem, Helmholtz, that is studied in Wang and colleagues. So here we're showing that by properly formulating the objective function, you would need significantly less number of collocation points for the boundary and for the domain to get a way better error levels. And now here is a multi-fidelity problem. This is discussed by Ming and Professor George in their paper Composite Neural Network. And so the idea here is that, okay, you have pressure heads here. So this is a soil column. You have pressure head, you have low fidelity data, high fidelity data, to make sure that these high fidelity and low fidelity data correspond to different levels of conductivity. Here I show both the corresponding conductivities, and you can see that the low fidelity data corresponds to a way incorrect low fidelity, incorrect soil conductivity. So anyway, and here we show that we only use one network because we use the maximum likelihood to extract information from low fidelity data, and we constrain the high fidelity data as equality constraints. And we only use one network for all of this. And here we show that that with multi-fidelity, where you use both low fidelity and the high fidelity data, you get a way better error levels, which is like 0.3%. And so, okay, now I've discussed all of this, and I'm sure there's a lot of issues that and questions I got. And now we thought, oh, okay, what about we apply it to everything and we think that it works for everything, right? But that's not always the case. We figured out that with neural networks, what we often do is we use automatic differentiation to calculate these derivatives. And what happens is that you're initializing your models randomly in the beginning, right? These models are initialized randomly. And obviously the predictions are random in the beginning. And so with these random predictions, if you take the automatic differentiation, do an automatic differentiation to calculate the derivatives and the second derivatives, then your noise gets amplified and amplified, and your loss function would get amplified. And now you have this very noisy loss function. You do another back propagation to take the derivative of this noisy loss function with respect to the parameters of your theta. And so what happens is that in some cases, these back propagated gradients could get so noisy that you just converge somewhere else, and you get this unpredictable training behavior and that your model wouldn't converge. And so we thought, okay, let's come up with a test problem, and we see that this canonical convection-dominated convection diffusion problem. And so this is studied in Van der Meer and colleagues. They showed actually that for a diffusion coefficient less than or equal to 10 to the minus 3 with adaptive collocation sampling strategy, none of their method and PINNs converge. And so we thought, oh, let's apply Pcon for this and see if it works. And actually, we found out that again, our twin models, but that for regression model, the model converges to the correct solution. And we actually made the problem even harder by setting the diffusion coefficient to 10 to the minus 6. And the PINN model diverges like this. So the PINN model turns out that because we constrain the boundary conditions are learned, but the pattern of the solution is not learned.
Sam, I'm a little puzzled because you compare with vanilla pins, which is about 8 years old now, as opposed to, let's say, pins with the self-adaptive weights of Negro from West of Texas. Why don't you compare with the adaptive weights?
That's a good question. We actually compared one of the benchmark solution, which is a lot simpler.
For this one, there's no need. There's no need to show something that we know, But there are a bunch of methods that work for this problem. I teach this in this example in my class. So, but there's a bunch of many methods that work with. Even if I put 100, let's say, not even adaptive, but self-adaptive weights. I don't know about 10 to the minus 6, but certainly for 10 to the minus 3, but I didn't try 10 to the minus 6, but there is a bunch of methods that work, but you sort of keep showing, I guess, vanilla pins, which we know they don't work. Even the early days, in the dark ages, Paris and Marja, they would use a bigger coefficient at the boundary. So that's clear. You don't need to. Your method is good. You don't need to sort of show with the comparisons to be against the vanilla, but the current versions. I think a lot of people come here and they made the same mistake. You're making the same mistake. Although your method is good, you don't need to kill a dead horse.
Thank you. But I honestly haven't seen any papers that are using like 10 to the minus 6 Squibb. I mentioned here the authors used up to 10 to the minus 3, and they showed that below that, none of their methods, their proposed methods and PINN worked. And so I thought, why not make it even more challenging and set it to 10 to the minus 6? And so I used 10 to the minus 6 here. But you're correct. I should have because there's a lot of methods getting presented, and it would be. I should do that.
A few weeks ago, we had a guy who was doing the singular perturbation, which is exactly what this. Okay, so with singular perturbation, you can do that also. So in other words, there's more than one way to slice a pie.
Correct. That's true. So
it would be more useful if you actually compare against contemporary methods, not the methods of 8 years ago.
Correct. Actually, this paper is also published recently. It's 2022. So, but that's true. That's a good suggestion. Thank you. I will definitely try it with other.
For this one, you have a comparison for 10 to the minus 3.
Yeah. Actually, so they say for below 10 to the minus 3, none of their method worked.
I can tell you 10 to the minus 3.
Below that.
I use that in my class. 10 to the minus 3, the self-adaptive weights work. Other people in the audience may have other experience, but
absolutely.
There's a standard self-adaptive weight with a min-max problem works.
Yeah. Sounds good. If anybody tried it for 10 to the minus 6, I'd be happy. I would be happy to know about that and discuss it. Yeah.
Then we also had just another one more component. Because we had Daniele Mortari from Texas A&M who does this theory of action connection. So he turns a constraint problem to an unconstrained problem.
Okay.
For any function, discontinuous and so on. So obviously, in his case, we get better accuracy.
Okay. Yeah. Sounds good. I'll be happy to know about that.
Standard there.
Sounds good. Thank you. Yeah, I'll be happy to know about that too. Of course. Yeah, and we're still developing these things. It's not like these are the end thing, but the end goals. But thank you for all those good suggestions and questions. So yeah, again, I want to highlight that this is 10 to the minus 6 diffusion coefficient, and we looked at their loss landscapes too. Turns out that for PINN and PCON, the model will settle into a little subtle like not a clear, the loss landscapes don't have like a clear minimum, even though for the pecan here, we do see a clear minimum, but the loss is so rugged, which doesn't really tells us that the model found a good local minimum, even though it looks like it's a good local minimum, but it's pretty rugged and chaotic. And then we went further and said, well, let's do a sensitivity analysis in presence of physics. And so how we do that is that we, once the model is trained, we get the solution, the derivatives and everything, and the back propagated gradients and everything. Then we perturb the weights of the model slightly. And then we again calculate the solution, the derivative, and the loss, and the back propagated gradients. And then we look at all of these things to see what happens if you have physics and you have slight noise in your weights. What happens to the predictions? How sensitive the outputs are to, and the back propagated gradients are to this noise. And so that's what we found out here, that so this is the weight of our model that's trained, and these are the gradients. And then, okay, C is, okay, so this is the distribution of the weights after it's perturbed. So now you see that these two weights are not too off. You don't want to add like so much noise to your parameter that the distribution will look totally different. With this small noise in the weights, turns out that the magnitude of the gradients increase several order from 10 to the minus 5 to 0.3, and even though the outputs don't show it, but the derivatives are totally different. So you can see that a slight noise in the weights may not change the output much, but it would highly change the derivatives, which tells us that these backpropagated gradients, when you have small noise, particularly in the beginning where everything is random, the weights are random and everything. So here we could propose better initialization schemes or reduce the order of the PDE so that we don't have to take higher order derivatives. And the same goes for pecan. And then again, for that simple convection dominated convection diffusion problem, we can now create what I mentioned at the beginning of my talk, an auxiliary variable. Or here, this auxiliary variable is nothing but a flux, our flux. And now we can constrain this auxiliary equation as well as our boundary condition. And we also proposed this other method, adaptive Lagrangian method. So it's pretty much similar to augmented Lagrangian method. But the main thing here is that now these Lagrange multipliers are getting updated with an adaptive learning rate, which is inspired by RMS prop. And all the details of these things are released in our GitHub code. You guys could go and try it out. But since I have less time, all I can say is here is that the learning rates are adapted with RMS prop. And for the same problem, we now see that, so this is the Lagrange multipliers for our flux equation or auxiliary flux equation. And now you see that the model is smart enough to know, oh, okay, near this origin, I had an issue with satisfying my flux. And so now I got to use larger weights for that to make sure that the flux is constrained at that region. And the model converges here with very good accuracies for 10 to the minus 6 diffusion coefficient. And again, we applied this approach for the transport flow, and here you don't have higher derivative. But here we're trying to show that you could use the adaptive Lagrangian method to like train these model with U fixed from the beginning. So the Aditi and colleagues proposed curriculum learning, which is nothing but increasing U from a small value to like large value during the training. Here we're showing that you can just set your U and constrain your boundary conditions and solve your problem. Because for a generic PDE, you may not know what governs the complexity of your solution, even though in this case you do know that it's U. I believe I have questions in the chat. Okay.
Yeah, some comments. We can look into this once your talk is over.
Okay. Thank you. All right. So I have a couple of minutes. All right. So now the conclusion. So in conclusion, the take-home message is that instead of like empirically or ad hoc tuning, we ought to first of all tackle the optimization aspect of PINNs. If you want to have a viable neural network-based solution for forward and inverse problem. And that means you could create better optimization, like adaptive augmented Lagrangian method, or you could have robust formulation that works for large-scale problems. You could have even physics-informed optimizers. You could have better initialization schemes. So these are like a few things that I believe if we, as a community, work on it, could help further the field. And we have several follow-up works on this that didn't make it to the presentation, but I'd be happy to share it and discuss it. All right, and with that, I move into questions.
So
Small viscosity. I think in the paper in the archive, you had the cavity flow. Did you try to do cavity flow at high Reynolds number?
Yeah, also that's a good point I forgot to mention. So what happens is when you introduce auxiliary equation, you're basically adding again several terms, and that also brings its own challenge to the optimization. So for some problems, you may think, okay, introducing an auxiliary equation might help, but for some other problems, it might not. I tried it for high Reynolds number. Turns out that lid-driven cavity, particularly for high Reynolds number, doesn't do a good job with the like introducing the auxiliary vorticity. I believe I introduced in my paper. Yeah.
Now, how about the augmented Lagrangian? Does that work there or not?
Yeah, we actually have a paper coming up with that, and it works for. But the thing is that as you increase
what Reynolds number?
1,000. So with Reynolds number 1,000, we try it, and what happens is that the model qualitatively get the solution, but the benchmark data by GIA, it can't really hit that. And then we show that if you add like 5 points, 5 like regularization labels, you could clearly get the benchmark results. Yeah.
So Mario has pasted in the chat the link for PINNs, which has been solved using theory of functional connections.
Right.
Maybe you,
My chat disappeared.
yeah, I can.
Okay. Sure, Eric. Eric has a question. Sure, go ahead. Oh, here is the chat.
Okay, yeah, sorry. So you keep talking about this initialization. I'd like to draw your attention to this paper by Nat Trask, where they did a different initialization scheme that preserved the kind of linear independence of the final basis for, in our case, I think we did regression, but I think we also maybe did a PINNs problem as well. And it was different than the classical, I forget what the name of these initialization schemes are. Yeah, Xavier initialization is quite different. It was designed more to work with ResNets, but it would also apply to more standard neural networks where your problem is you basically get a collapse of the basis functions at the end. Anyway,
yeah, that's great to know.
I'm happy to share that with you. So
yeah, absolutely. I'd love to know about that. That sounds interesting. And I have two.
Hi, Shams.
Sure.
Can I have a question? Thank you very much for the nice talk. It was very insightful. I would just like to know if you're keeping track of the convergence history of your accuracy, because as George mentioned previously, currently there are multiple emerging methods and schemes for accurate results and accurate convergence, but it would be interesting to see how fast this scheme converges to a relatively good accuracy. Do you have such results, or?
Yeah, actually not on the paper, but if you go to my GitHub code, at each, I believe, 500 epoch or something, I output all the accuracies to see how accurate the results get as we do the training. But I didn't report it in my paper.
But as an order of magnitude,
Mhm.
on average, how many iterations would your model require to converge to the minimum loss?
That depends actually on a lot of things. First, it would depend on your architecture, optimizer, and your PD. I can't really like give you like a rule of thumb to say, well, at this epoch you get a good solution. That would be.
I'm asking, it's just on average, like to get a perspective, because, for example, the problems that they solve in the DASA pins, for example, and they get an impressive accuracy, they require the order of 100,000 iterations. Is that similar to your order?
Oh,
or?
no. All of my problems that I have, it's either 5,000, 2,000, or like 10,000. Yeah,
Okay,
they're
that's what
not
I'm asking.
100,000. Yeah.
But the problems you showed, I think they were mostly 1D, right? So
Sorry, problem.
the problems you showed in this talk, they were mostly 1D problems. So I assume that this will reduce the
No.
iterations.
I have
But
for this presentation. I only showed like simple problems that I could explain for the talk. But if you go to paper, I have like two-dimensional problems too. Like I have lid driven, and there's a few other problems.
okay, I'll check the GitHub also to see the
Sure.
convergence.
I'd love to get feedbacks, try it for different problems, and let me know if it doesn't converge, or because I want to know too.
Sure, thank you.
Yeah, thank you.
I think Professor Erhard wanted to comment something.
Sure.
Yeah, thanks. It was a very nice talk. I have more a general comment, maybe in the spirit of what George said. So I was thinking I was addressing this convection dominated problem, but in general. So if you go back in time, what George said, then so these original pins they are already quite old. So you have a neural network, and you are supplying this network with the information of the residual of the PDE. This is somehow the old story, and now the next generation should be what else information can we supply to the network instead of just stupid learning. And so here, for example, if you, I mean, my idea is to give more mathematical information on the solution structure to the network. So for example, if you just increase the frequency like you did in this omega, of course you get more noise. But if you, for example, would tell the network what is the frequency, then you can do some scaling, and then it would become again easier by a simple mathematical trick. Yeah, so I mean, there are a couple of approaches, of course, perturbation, WKBJ, mimetic schemes, or for example, with this problem, you can also try a total derivative, so that you are computing the solution not on the grid point, but on a trajectory that is defined by the total. So there are many mathematical tricks where you can help the network to have a simpler problem to solve. Yeah, and I think this should be, I mean, this is already the future direction of PINNs.
Yeah, those are great suggestions. I would love to work with whoever it's trying to like bring mathematical like techniques and these things to make the field, or to further the field. I'm myself a student of this field, and I love it. And these suggestions are great. I'll be happy to work with anyone, and I'd be happy to discuss, to take this offline and discuss it further, and get your brain on it. And yeah, absolutely.
Thanks.
Thank you.
I think we have a question from Senagok. He wanted to know if the same network is being used for domain and the boundaries.
For which problem?
He may want to ask. I don't know if he's online. Senukuk, if you want to talk, you can ask your question. Yeah, I think he's not there. And Eric just pasted the paper. Okay, it's your advisor.
Okay. Could you please like send these chats to me after the talk? Because I would love to like check out these papers and get all these nice messages and you know
I can
think
send
about
you
them and
the paper links. I can send that to you.
okay, thank you.
And
Thank you.
also, Eric just send the paper for the initialization.
Yeah, absolutely. Thank you, Eric. Thank you, Eric. Thank you, Matthews. Thank you, Professor George. Thank you, everybody. Like I got really nice suggestions and good questions. It's actually mind-blowing to me that now we have this field and a lot of great researchers from all around the world here discussing ideas, sharing ideas, and that's great.
So are there more questions for him? Okay. If not, thank you, Shams, for this wonderful presentation, and thank you for tuning in today.
Thank you so much. Thank you for having me. Thank you, Professor George, for inviting me. It was an honor and a pleasure to meet all of you here. Thank you so much. I hope I added something to the field and looking forward to the future. Have a great day, everybody.
Thank you. You may want to stay
Right.
for the second talk.
Okay. Sounds good. Sounds good. Sure. Thank you.
So we move to
So it would be with the same Zoom link?
yeah, we would continue from here.
Oh, okay. Sounds good. Sounds good. All right. Now, I am so novice at Zoom and I don't know how to get rid of these pointer and
You can just stop sharing.
okay. Screen and show maybe. Okay. Oh, here it is. Stop. All right. Thank you so much.
So we move into our second speaker, Ali. You may want to share your screen while I introduce you to the audience. Okay, so our second speaker is Ali Khashefi, Dr. Ali Khashefi. He would be talking to us about ChatGPT for programming numerical methods. Ali received his MSc in Mechanical and Civil Engineering and his PhD in Civil Engineering from Stanford University. His research interest lies in computational mechanics and deep learning with a focus on irregular geometries. With that, please welcome him for the presentation. You may want to start.
Yeah, thank you, but I'm not sure if
You can go to the presentation mode.
can you see my screen or not?
I can see your screen, but not on the presentation mode. I can see the PPT.
Trying to do so, but I face an issue, unexpected issue. What we can do? Let me stop sharing and then maybe share again. Yeah, actually, I received an error from the Zoom. May I send you my slides to your email and then you can share it and then I can talk to them, right?
Presentation. Dr. Can you just resume the recording once more? I just paused it.
Yeah, I already did.
Okay. So you can start, Ali.
Okay, thank you. Thank you, everybody. Sorry about what happened, but right now we go here. ChatGPT for programming numerical methods. At the beginning, I should say that it's a little bit casual talk rather than full technical talk. And I'm talking about this thing that recently we first published on arXiv, and then right now it has been accepted in Journal of Machine Learning for Modeling and Computing. So next, please. Yeah, just a breaking news. A few days ago, ChatGPT boss Sam Altman questioned on AI safety in the US Congress. And then there were so many concerns about unemployed people, future job, the next US elections, and about the children. Next. I would like to say a few sentences about Sam Altman. So he was a bachelor student in computer science at the Stanford University, but he dropped just after the first year right now, but he's the angel investor of Airbnb, Reddit, Pinterest, and so many other companies. And also he was an invited lecturer for a course of how to start a startup at the Stanford in 2015. So the course is online on the YouTube. If you are interested in starting a startup, that course might be helpful to you. Next. Also, we had a Time magazine that talked about the ChatGPT. This is a cover of Times a few days ago. The question is that it asked ChatGPT, what do you think of a Time cover story with the title, "The AI arm race is changing everything"? And next, actually, I asked the same question, and then I got a little bit different answer. And so you can also try it in the ChatGPT to see what you can get. So ChatGPT, GPT is generative pre-trained transformer. But before we jump into the ChatGPT, I would like to also introduce a few other generative models that are hot topic nowadays. ChatGPT, Microsoft Designer, Audio GPT, Auto GPT, Leonardo, Bard by Google, Lava, Llama, Midjourney, and let me show a few examples. Yeah, so I was thinking to prepare cover for the cover of my talk. So I used the Microsoft Designer. So the input is a description. A robot is coding at the Stanford University in open space with a sense of crime in an old-fashioned style. And this is something that we get from the Microsoft Designer. It's free. You can try it. And in terms of the honor code, ChatGPT debated yesterday at the Stanford University by the administrative office. We can also do some other thing. We can connect those generative tools together. For example, we can generate idea using ChatGPT and then give the idea as an input of the Microsoft Designer. So here is some example. If you have a jungle in your home, there is an office under the water. Some fish are flying over the sky of the New York City. Next, please. And so you can do something more fun. You can generate idea and then give it to the Microsoft Designer to generate an image, and then it tells you a story using the Lava. Lava is also free. I gave an idea, and then this is the image that generated. You can see that, and also I copy paste the text. But there is some serious point inside of the story. If you go to the next, please. Yeah, the highlighted part. So the pirate AI is too bufferful and has already infiltrated his mind, accessing his memory and experiences. So at the end of the story, we realize that the AI tool is killing the human. And then at the end, we can read, this chilling tale serves as a warning to those who dare to delve into unknown, for the price of knowledge may be greater than one is willing to pay. And next. So there is a caution that context generated by AI can be inappropriate. We should be careful when we are using that. You can use also Midjourney. I did something fun with physics informed neural network. If you go to next slide, please. Yeah, so this is an image of the physics informed neural network recently published by your research group. I took the image and then gave it to the Lava and then asked it to describe this photo. Next, please. Yeah, and then in the text, we realized that it understands it's a neural network. There are some nodes, there are some flowcharts that connected together. And then I gave the text to the Lava to the Midjourney and asked that to generate a picture based on this description. This is the image. It's generated by Midjourney. It's not too much relevant to the original picture. But anyway, so just as a last point, and then we go to the ChatGPT for programming. So there are lots of people, even professional people. For example, Mehrdad is a famous art director at Walt Disney, and he's famous for so many animation studio work. And then if we go to the next slide, so he recently asked people to just contact the US senators that stop using AI. So because they have a concern about losing their jobs. Anyway, so this brief introduction to the world of AI nowadays. So some question about for us is that, can we write or generate textbooks? For example, if you want to have a textbook using computational fluid dynamics, just using these different tools, right? We can generate codes, text, pictures. Or a more question is that, do we need even textbooks anymore, at least in the current format, or we should think about other type of books? But if we think about codes as a specific type of text, so can AI generate codes for scientific computing? That it's what I have done. Yeah, ChatGPT for programming. Next, please. Yeah, as I mentioned at the beginning, we first wrote a technical report and then uploaded an archive. Next, please. This is a long, relatively long report. We discuss a variety of things, and in this talk, I mentioned a few examples. But what I would like to again mention that once I uploaded the report on the technical on the archive, and then the ResearchGate can catch it. So we can see that just in 2 months, I got more than 4,000 reads for this publication, more than 100 people recommended. And you can see that, and yeah, just in 2022, the number of my reads is just around 1,500. But after uploading the manuscript, it becomes around 5,000. So it got lots of attention. My point is that lots of people are interested in this topic and are using ChatGPT. Next, please. Yeah, we publish it. It's in the Journal of Machine Learning for Modeling and Computing. And just in 2 months, we got 7 citations for these publications. And next, please. Once I decided to also distribute my report, so I sent email to some professor that I thought that maybe they would be interested. I was a little concerned about that, but I got lots of positive feedback. So Professor Ohadi from Caltech, George Karniadakis at Brown University, Professor Hughes at UT Austin, Sarah at Stanford, Professor Fetkov, Department of Computer Science at Stanford, Stephen Boyd, he's in Electrical Engineering Department at Stanford and in area of the optimization. So they gave me back by emails, and then they were very exciting, and I'm happy about that. But specifically, I would like to share with you what Tom Hughes wrote to me. So he's definitely a famous person in computational mechanics. He's chairing computational applied mathematics at UT Austin. Before that, he was at Stanford. So he wrote many books. And then this is the email that I got from him. So that's great, very exciting. I cannot wait to share with my group. Couple of questions. Have you thought about doing same for artificial neural networks? I would like a quick and easy way to generate neural networks using different idea without the hassle of building codes and testing for each idea. If you could figure out how to get ChatGPT to do the testing, that would be so good and to be true, but one could always hope. And he sent another emails to one of his colleagues and then just CC me. And I would like to share it with you. Check it out, it's very interesting. The next numerical differential equations course will certainly be using ChatGPT or something similar, as with many other courses in EM and other institute. And then he said that I think we seriously need to rethink the math courses for that and other reasons. Perhaps the time is now. And he believes that using the ChatGPT, we can propose the courses at UT Austin somehow differently. Next, please. And also there is prompt engineering. So the question is that when you have a ChatGPT, how you should ask question. So there are some online courses that I just listed here. If you go to the next one. Yeah, it's a course by Texas Austin, also by deeplearning.ai or by Udemy. I didn't try any of them, but
are you planning to talk about the subject of the talk or
yeah, sure.
Okay.
That's the end. Yeah.
Okay.
Yeah, I mean, this is about the multidisciplinary research for ChatGPT. Yeah, maybe you are not interested in that, but anyway, the idea is that we can use ChatGPT for combining different ideas, even if you have some very distinct stuff together. So it could be useful for multidisciplinary research ideas. But anyway, let's skip that. Yeah, skip that, please. Escape, please. Okay, so here's the examples from my technical reports. So example one. So if you go one slide back, please. Yeah. One. Yeah. Okay. So specifying numerical problems. So we have. I would like to show that the capability of the ChatGPT, and then how, when we ask ChatGPT to solve a problem for us, how much we can specify the details. Yeah, so as a first example, I just write a Python code to solve the 2D Poisson equation and plot the solution. And that's it. I didn't say anything else. And then it wrote the code and then gives me the output. But next, please. In the next prompt, I specify the source term. Write a Python code to solve the Poisson equation with the source term of sine of x star cosine of y. You can see that how much it is simple. I mean, it understands star means times, and again, it gave the code and plot the solution.
Actually, is this GPT 3.5 or 4?
For most of this, I use 3.5, but I try. I mean, at the end, I address some issue. The issue exists even in 4. I try it.
Okay. Okay.
Yeah, but for these simple problems, both version works. So next one is about. We can specify more. We can specify the boundary condition, the size of the domain, and something is interesting.
Oh, by the way, Ali, this is Lulu from UPenn. I have one small quick question. So have you tried to copy the code into, let's say, run the code? Because I have also tried sometimes for the write code from ChatGPT, but in many cases, there are always small errors you have to fix manually.
Yeah, okay. So for the report that I presented here, the code works fine. I didn't touch the code. I just run the code in the Colab and then works fine. But there are some cases that the code doesn't work, and I will show those cases.
Okay, thank you.
Yeah, but I mean, for any case that I say that it works, it's just the code produced by ChatGPT. I didn't touch it. So something is interesting in this problem is that I said that use the zero Dirichlet boundary condition for x is equal to 2.5 and x is equal to minus 2.5. And then the gradient of the variable is 0 on the other boundaries. So the ChatGPT first explained the problem, and then at the end it says that and 0 Neumann boundary condition for y is equal to minus 1.5 and blah blah. So it understands that the 0 Neumann boundary condition is equivalent to the gradient of the variable is 0 on other boundaries. Anyway, so that was a simple example. The next one is machine learning, physics in for neural network. I made a very simple example. So write a Python code for finding the solution of the partial differential equation of, okay, so you see U underline T. It understands that U underline T means du dt. And also you can write du dash dt, but it's smart to understand that. Is equal to U again underline xx, the second derivative of the U with respect to x, plus some source there. Using the PINN methodology, you see that I didn't mention physics in for neural network. I just wrote PINN. And when it explained the problem, it says that to solve the given partial differential equation using the physics in for neural networks. So somehow it was interesting. Yeah. And then it produced the codes. I mean, all of the codes are also available on my GitHub, so you can take a look at the code or play with the code. So, yeah, I mean, this is a very simple problem, but anyway, the solution is correct. The predicted solution versus the exact solution. I mean, they graphically looks the same.
Have you tried an L-shaped domain?
No, I just try a simple domain.
Oh, okay.
Yeah, I look at the question. I will talk about that when we go to the Navier-Stokes equation. So, yeah, machine learning for convolutional neural network. So I asked it that develop a Python code for prediction of the velocity and pressure field around airfoil with different geometry. Use convolutional neural networks. I specify the size of the input, and I didn't have a data, but it generates the neural network. First, it explains how the structure of the network should be implemented. It generates the code. But there are two interesting things that I would like to share with you. Next, please. So, I mean, we know that convolutional neural network is an idea for image processing initially in the computer science department. So I asked CNN for prediction of the velocity and pressure field. So in some line of the code, when it wanted to specify the loss function, it says the loss is equal to MSE, a mean square error. So it realized that the loss function it's something mean square error, which is a quantified error measurement. Yeah, just go back to the previous one. Yeah, thank you. And another thing is that in my prompt, I just said velocity and pressure field in 2 dimensions. Okay, that's it. In the last layer, when it wanted to go to the get the output, it specifies 3 channels for U, V, velocity, and also pressure. So it understands that velocity in 2 dimension has a U and V components. So that was interesting to me. I wanted to share with you. The next example is about debugging and improving codes. So I had a C++ code for solving a system of equation using the Gauss-Seidel method, and I copy paste my code into the ChatGPT. And here you can see some part of my code. Okay, so this is still my own code that I copy paste to ChatGPT. And at the end, this is the main function. Yeah, I mean, I would say to you next and then go to the next one. Thank you. So in the main function, we can see that we have I give it a test, right? AX is equal to B. I build up a matrix B and matrix vector B and matrix A, and to just check my code, if it works or not. Next, please. Okay, so this is the answer by ChatGPT. So the code for solving a system of equation looks fine. And you can see that it builds up the equation that was exactly in my code, right? So 6x1 plus 2x2, blah, blah, blah. And then it understands the actual solution is, for example, x1 is equal to 1 and blah, blah, blah. This is interesting to me that it seems somehow the ChatGPT run my code and then it produced the outputs for me. You see, at the end, x naught is equal to 1.003, x2 is 0.999. I mean, it was a little surprising for me because if it's just a generative model, how it access to the some compiler, some C++ compiler, because it can run my code and then say that, okay, this is the output of your code. Very simple example, but there was a insight for me about that. Next, please. Okay, but my code works fine, but I intentionally put some errors inside of my code. In some line, I just, instead of that, in a for loop, instead of indexing from 10, I put 0. Instead of 0, I put 10. And then again, I just copy my code to the ChatGPT and ask it if it works fine or not.
Sorry, Ali, could you go back to a previous slide? So I have one question. If you run the code by yourself, is this the answer you get? 0.0003? Because I would expect you can have more accurate answer than this if you really run the code. Probably 1.0000003.
Okay, I guess it depends on the because it's a loop, right? It means that when you stop the iteration.
Yeah, basically run your code, right? If you run your code by yourself.
Yeah, my point is that, I mean, the main reason that it gives the output like that, it's 1.003, is that because I think inside of my loop, because we specify criterion when you goes outside the Gauss-Seidel loop. And then, for example, it's say that the error is 10 to the power minus 3, then you got something like that. But I can try again to make sure that if it happens or not.
Yeah, the reason is I have seen all the other cases. So the ChatGPT seems running some code, but one possible explanation is it did not really run the code. It tried to guess what the output of the code it is.
Maybe, I don't know. But I mean, in the previous part, you see that it says the actual solution is x1 is equal to 1, x2 is equal to 2. So I'm not sure if this is a guess or it's, yeah, I don't know. But thank you for comment.
Yeah. Sure.
Yeah, next please. Yeah, I was talking about the error and then next please. Yeah, it catch the error. So it says that indexing of the loop index for I start at 10, which doesn't make sense since n is 5. So it should start from 0. And it suggests other comments for improving my code, and it rewrote the code and then gave it to me. That was nice. Yeah, next please. So completing incomplete codes, I think it's an easy one. Next please. Yeah, so I said that, okay, I have written C++ code for solving a tridiagonal system of equation. There is a specific part of the code that I don't know how to write it. In fact, inside of the loop of 1, can you help me and write inside of the loop? And then I just copy paste my code, the whole code. And this is, I'm showing to the for loop that the inside of the for loop is empty. I mean, it's a very simple example, but I'm just sharing with you what I have done. Next, please. Yeah, it's immediately realized that inside of the loop should, what should be inside of the loop for a tridiagonal system. And it rewrite the code and then gave you the complete value. Next, please. Okay, so so far we discussed the. There are some other benefits that I didn't talk here. I'm just listing that. So, for example, it can it has ability to write in code in different languages. So C, C++, Java, Julia, MATLAB, Python. Also, if, for example, if you have a code in C++, you can give it to that and then ask it, okay, to rewrite the code in a different language. So it can do it for you. There are some examples about that in my code, in my report. Also for C++, for some simple C++ code, it can do code parallelization using, for example, MPI. And yeah, so, but here I'm switching to the issue of the ChatGPT. But yeah, thank you. So here is an example that I face an issue. Please write a Python code for solving the 2D diffusion equation using the alternating direction implicit method. And it gives the code, but when I ran the code, next please. So at some part, when it wanted to compute the inversion of the matrix, when I run the code in the for example, in the Google Colab, it says that it's not invertible, singular matrix, which is very bad. So I mean, for many engineering problem, we eventually wanted to solve a system of equation like x is equal to b, and but that was the case even for a simple 2D diffusion equation problem. Next, please. The next one is generating array with incompatible size. Next, please. Yeah, so write a MATLAB code for solving the two-dimensional incompressible viscous flow. As a test case, use the lead-driven cavity problem for the Reynolds number of 100 and use a pressure correction scheme. So it generates the code using the pressure projection scheme and for lead-driven cavity in the MATLAB. Next, please. But when it wanted to compute the divergence, it produced two matrices, U underline X plus V underline V, which is du dx and dv dy. But in the MATLAB, we gave the issue of arrays have incompatible sites for this operation. Some similar issue I also face for when I asked to write the code in Python. And usually we face these problems when we have a gradient. For example, here we have a divergence. That's unfortunate. Next, please. Yeah, when the problems becomes a little bit complex, it starts using some library that probably you don't want to use that, or even it's some of them are unknown. Here I mentioned 2 examples. Next, please. Please write the C++ code for solving AX is equal to B while A is a general sparse matrix using the Generative algorithm. And then you can see that at the beginning of the code, when it says include, so it's immediately start using the IN library, which is somehow famous, but I didn't have any intention to use those libraries. But anyway, that is something you may face. I got a question about the staggered arrangement of the velocity and pressure field. Okay, I don't remember currently. I have to look at the code. I mean, the code is also online. But sorry about that. I don't know the answer right now. Next, please. And also, it's write a C++ code for generating triangular mesh that can be used for a finite element solver. And again, at the beginning of the code, you can see that it includes triangle.h. I mean, I even searched online. I couldn't find this library. There are some library for triangle, but I mean, it just includes a library that it's not famous. It's not obvious that where we should get that library, and it's annoying. Next, please. Yeah, server disconnection that I think one of the audience has mentioned that. Yeah, so all of the problems that I mentioned so far was very simple, basic problems that I think nowadays nobody cares about, and maybe it's just useful for students who want to take some numerical courses. But for some serious problems, we face some serious issue. One issue is that it stops coding. Once the code becomes a little bit long, it stops coding. So here is an example. Next, please. Yeah, this is my prompt. So please develop a C++ code for solving the 2D incompressible flow. Use a pressure projection scheme. Consider the 2-dimensional Taylor gain vortex with periodic boundary condition as a test case. It's explaining the code and start coding. And next, please. At some point, you see that in the first panel, you see that the for loop for int I is equal to, and then it stops. Something that I learned that I just ask it, okay, please continue coding, you stop. And then it says, apologize for that, and here is the rest of the code. But the rest of the code is not necessarily from the end of the previous part. And it happens again and again. And eventually, I mean, it was frustrating to yeah, that's also an issue. Even for 2D incompressible Navier-Stokes equation, to us, it's not very challenging code, but ChatGPT, even ChatGPT 4, I would like to mention that, still suffer from this issue. Next, please. Yeah, I just wanted to summarize some positive aspects is that it can write program in different languages. It can debug and improve the codes. If you have incomplete codes, it can make it complete. If you have a code, it can switch to a different language. a code parallelization, a code explanation. It is something that I didn't mention in my report, but I would like to mention it here. So for example, I'm interested in machine learning and deep learning. So I would like to use some codes that developed by some CS students. And I'm going to the GitHub, read the code, but because my background is mechanical and civil engineering, at some lines of the code, I face an issue and I don't understand the code. I would like to learn it. So I copy paste the code to the ChatGPT and ask it, okay, what the code does at this line, give me some example, give the explanation. So it can be like a teacher. I found it really useful, especially if you wanted to learn a code that's written by some other people, especially in the area of the deep learning. Next, please. Next, please. Yeah, and then challenge, singular matrices, array with incompatible size, including unknown or unwanted libraries. Refusing to write in code, actually this issue has been resolved recently. So we should know that the ChatGPT has been released just in November last year. It's less than 1 year, and there is a hope for improvement. And just some key points as the last slide is that we can think about ChatGPT or other language models is beneficial to scientific computing, but definitely there are some certain limitations, especially for some serious problem or some problems that requires long code. And there is a hope for improvement. I would suggest that stay up to date. Nowadays, new tools will be introduced and will be released. So it's important that we learn these tools for our research and speed up. And we expect that the academia becomes a more competitive environment. So we can spend more time on critical thinking and developing idea rather than just coding. And some other hot topic today is that AutoGPT or AI agents. So maybe we expect that the incremental research can be done by AI agent. So so it shows that the revolutionary research becomes even more important. That was my talk. Thank you for having me.
Questions for him? Thoughts, maybe? Yes, Nicholas.
Hello, thank you for your talk. I was wondering if you had like the chance to play with like different plugins, either like the work from Alpha, like for mathematical operations, or like full Visual Studio Code if they give you better answers to work answers.
Yes, I couldn't hear you clearly. I mean, if
so can you hear me now?
Yeah.
Better now?
Yeah, right is better.
I was wondering if you had the chance to try like other different plugins that they advertise, like the one with Wolfram Alpha, or like through Visual Studio Code, if they give better code, better mathematical operations.
Okay, I tried Bard by Google, and it's actually it's very off. I mean, compared to ChatGPT, it has nothing to say right now, and it's in experimental version. But yeah, I tried that tool. I didn't give something exciting.
Thank you.
Sure.
Nicholas asked about Alpha Wolfram, where they have that's supposed to do scientific computing with ChatGPT together.
Yeah, I have heard about that. I didn't try it.
More questions?
Can you hear me now?
Yes, Adar, go ahead.
Oh yes, I'm sorry. I was trying to speak before my mic doing some problems. I'm Adar from Brown. I wanted to add to this discussion. I've been using GitHub Copilot for a while now. I do find it pretty interesting. Sometimes it like completely flops, but sometimes it remarkably completes some subroutines that it does it exactly as I wanted, and it's really pretty nice. So talking about like those add-ons and things, some of them work pretty decently.
Thank you.
More questions or thoughts?
There are some questions in the or remarks in the chat. I don't know if Ali has seen it.
Sure, I can take a look.
Umair has a question.
Pardon me?
Umair, I think he's also online.
Often ChatGPT stop midway. Yeah, I mean, I addressed this question that I agree with Omer that ChatGPT stopped mid while processing code. It was about the Navier-Stokes equations. Yes, absolutely. I came across the same problem. Next one about was, did ChatGPT use the staggered arrangement of the velocity and pressure variables by itself? I didn't remember. I have to look at my codes. Sorry about that. And Matthias, for triangle library, yeah, sure, I can try it, include that library to make sure, to see if it works or not. But I mean, the point is that when we ask ChatGPT to do something, we would like to get the perfect answer because we want to speed up our work. So, but thank you for sharing the link. Are you using a paid account or, yeah, okay, free pausing code is a similar, okay. ChatGPT 3.5 is free. ChatGPT 4 is $20 per month. I have both versions. I'm using the paid version. The issue of the pausing the code is also in the ChatGPT 4. So even if you pay, still you face the same issue.
Ali, I have a question on the verification. So let's say you did the even the Gauss ideal and you get an answer. Can you ask it to verify, or let's say the cavity flow? If you do the cavity flow, you ask it to do the cavity flow using write a code cavity flow. Can you ask ChatGPT to compare against the either fabricated solutions or exact solutions if they're on the web, or other solutions that are out there published? Did you try to do something like that, verification?
Okay, so I mean, first point, unfortunately, ChatGPT couldn't come up with the Navier-Stokes equation. So I tried the cavity flow, it didn't work very well. But I understand your point. The point is that you can ask it to write a code for you to do the verification, but it doesn't the verification itself.
Okay.
There's a question by Kasha. She wants to know the benefits, if you have noticed any benefits between using version 4 or version 3.5.
Okay, I mean, for machine learning problems, I had an easier life with version 4, but it was just a personal experience. I mean, yeah, for other stuff, definitely 4 is better than 3.5. But specifically for coding, I didn't see any significant difference. 4 is slower than 3.5 in terms of generating. 3.5 is faster. Maybe that's the it's one positive 0.43.5, even it's free. Sure.
If there are no more questions, thank you, Ali,
Sure.
for coming today and for giving us this talk. So with that, we come to an end of today's seminar. I would be uploading the video on our YouTube channel, so please follow us over there. And for all of you, have a great rest of the week. Have a great weekend, and we'll meet again next week. Bye.